people still joining. I'm very, very excited. Susan and Matthew are TAs at University of British Columbia teaching systematic program design. Is that a good way of putting it? Is that what you're okay? So the approach they're taking is I've probably mentioned it a few times. I think I've showed it to people here. The how to code simple data, how to code complex data that's on edX, and what they're doing follows something similar to that, which we'll find out more how similar here in just a minute. But anyway, I'm very excited to have them come join today and just talk about what it's like trying to teach people how to think programmatically, how to solve problems in codes, and how to lay a foundation for being successful with a software career. So I think there'll be a lot of takeaways for people that are in software now. Probably a lot of takeaways too if you have a young person or someone that's interested in working with code. And hopefully Susan and Matthew will have some good takeaways for how to advise people in a very rapidly changing industry. So turn it over to Matthew and Susan. And thanks so much for coming. Very, very good to have you guys here.
Thanks, Mark. I'm going to start screen sharing now. All right. So hi, everyone. I'm Susan, and this is Matthew. And we're part of the teaching team for ComSci 110 at the University of British Columbia. The official title for the course is Computation Programs and Programming, which doesn't describe that much. But essentially, it's our introduction to computer science course. And like what Mark said, this course is about teaching systematic design. So not just about how to write code, but how to approach problems with the same mindset that experienced programmers use. And I'm going to take you to the next slide, where someone who will explain more about what we do in much better terms than I ever will, the creator of the course, which is Gregor. Oh, I just wanted to do that real quick.
Hi, my name is Gregor Cazares. I'd like to tell you about our Introduction to Systematic Program Design course. I'm really quite excited about this course because I spent my whole career working on how to write programs where the code looks like the design. And that's really what this course is all about. Our goal with this course is for you to be able to design a wide range of programs using a variety of languages and in a variety of problem domains. By that, we mean programs that implement things like games or simple animations or data analysis and graphing, crawling the web for certain information, data integration, and many others. And that are written using languages like Java or Python or MATLAB or C# or JavaScript. Now that may seem like a lot, but I think it's what you should want to get out of an introductory course. Because you may want to write one program in one language today, but once that's done, you're going to want to write other programs in other languages tomorrow. And this course has a unique structure that makes it possible for us to deliver all that. So let me talk about that structure. First, this course presents a design method. Now, a design method is a repeatable process that lets you go from having a poorly formed problem, say, I wish I had a Pac-Man game, or I wish I could crawl part of the web to collect certain information, to having a well-formed solution. In other words, a well-organized and well-tested program that you know does what you want. The method works for the kinds of programs we will design in this course, and it will also serve you for more complex programs you design in the future. So in this course, you won't be learning techniques that work for introductory problems. Instead, you'll be getting an introduction to a method that you can use on any hard design problem you face in the future. This is a crucial point. This method is not a toy. It is grounded in work by Michael Jackson, Matthias Feliason, and others. And what I can honestly tell you is that when I have to produce a program that seems hard for me to design, what I do is I fall back and use this design method to design it. Another key element of the course is that it has multiple tracks. The introductory track presents the basic design method and uses a simple teaching language. In this track, we'll work on designing programs that implement things like simple games, organizing picture system, and the track culminates in a simple Pac-Man game that you could even run on your Android phone. At the end of the introductory track, the course splits into tracks that work with different popular programming languages and focus on different specific problem domains. At the end of all of the tracks, we're going to show you some of the programs that our former students have gone on to design using this method. Now, each of the second phase tracks builds on the core design methods in similar ways. So when you get to the end of any one track, you will have covered the whole design method. If you want to see more examples, or you want to see how the method works in other languages, you can go back and follow another track as well. You will, of course, be able to go through each additional track much faster than the tracks that you've already gone through. Now, even if you follow just one of the second phase tracks, you will have seen how to adapt your skills to a different language from the one you started in. And that's a crucial skill. Again, you might want to program in just Python today, but you'll want to program in a different language soon. So in summary, what's different about this course is that we present a design method, and we use a multi-track structure to allow you to bring that design method to multiple specific languages and problem domains. So I hope you'll join us for this course. And even if you end up taking another course between now and then, you can come back and learn this design method afterwards. Come back and take this course later. Many of our former students already knew how to program and ended up saying that they were better programmers after they took this course.
So a quick disclaimer about who we are and what we're not. Obviously from the video, neither of us are Gregor. We're not professors. We're just a couple of undergraduate computer science students. But the reason why we feel at least prepared in a position to present this talk and talk about what this course provides is because as undergraduate TAs of the course, we are in a very privileged position to have a lot of say in how the course is run and how it's structured. And we contribute a lot in terms of just ensuring that the course is in its best position to give the students what they deserve and the best experience that they can take away from this. We have a couple of other lead teaching assistants, some that manage the course infrastructure, including the AutoGrader server. And we also have a couple of other teaching assistants who manage the data science end of it, like learning analytics and analyzing cases for academic misconduct. And we're the small group of lead teaching assistants that manage the teaching end of it. So we make sure that the labs that are run by the other TAs are well run and that the office hours are seeing good use from the students and that they're being run properly. And in addition to that, we meet up with students around campus to ensure that they can get the extra support that they need for this course. But we're certainly not industry experts. We have some co-op and internship experience as university students, but that's the extent of it. Any answers to like industry things, Mark will have much better answers to that than we ever will. But what we do hope is that our different perspective on this course that's different from what a professional or a professor would have is still helpful, mainly because of the students that we teach, which we have a very diverse student base as a very large public university. We have a lot of students from overseas. We have a lot of students from Canada, but it's like a really good mix. And not all of our students come in with programming experience, since this is a first year computer science course. And not every student comes into our course hoping to go into computer science. A lot of them are here just to fulfill major requirements or to just learn some more about computer science and decide if they're interested or not. But a really big aspect of that is that, one, we want to make sure that we have a level playing field for our students as they come into the course, so that everyone is primed and prepared to succeed. And the other thing is that we want to make sure that we get this first take at their first ever computer science course right. And we want to ensure that even if they didn't come into this class hoping to go into computer science in the future, we still want them to take away something from this course that doesn't necessarily have to be computer science. And a big part of it is learning how to solve difficult problems following a systematic method. So it is a big responsibility on our end, and it is a privilege because we know how much of an impact we have, just not just on the students that we teach, but also to the greater society as our students move on to go work in various fields, and we want them to take away what the message that we're trying to impart. with this course. And ultimately, we're not trying to just be a good course. We're trying to be the best course that a public school of this size and this population can offer. And we very strongly believe in what our course presents. So what we teach is our course focuses on teaching a set of design methods that enable our students to design small but very difficult programs. And this course is based on the work of Matthias Fliesen, specifically his How to Design Programs book and his curriculum. And in a big school like UBC, there's not much of an emphasis on getting student support because it's not very feasible for a very large course. We have like 1,000 students in our first term that we have to teach. And the way that this course is formed, and as you can see from the content that we cover, it demands a lot of work, but really we're trying to that doesn't change how we choose to approach the way we teach this class. We still try to provide every single resource we can, and we want to really prime these students to succeed. And one of the ways we try to do that is by trying to remove any barriers that might be associated with CS and might make it difficult for students coming into a computer science class to succeed. So some of our most experienced teaching assistants are non-computer science majors, and it is important to present that to the students so that they can see that not everyone here was a CS person and succeeded in this class. And they additionally have that background of not programming that they can use to connect with the students and teach them all the better and support them better. And we avoid using additional technical jargon that's not covered in the course. A typical answer we'd have to questions that like students with program experience come in with to like normally, I don't know Java, I don't know Python. That's not what we're teaching in this course. That's not what we're covering in this course. And the last thing is that keen students are a great addition to any class, but we try to avoid getting into overly technical conversations with keen students in front of other students so that we can mitigate any imposter syndrome feelings that can result. And I'm sure, as most of us know, it's very impactful to how someone can perform and succeed if imposter syndrome becomes a thing. So we're really trying to limit that in our course. That's enough talking from me for now. So I'm going to pass this off to Matthew, who's going to give you a bigger overview of the course and what we do. Matthew?
Thanks, Susan. First of all, I'm very nervous to give this talk because I'm a typical computer science major student, and the reason why I'm able to talk as I'm talking right now is because I have TA'd and that gave me a lot of experience in public speaking because I had to talk with many students and many at the same time. So I'm going to try my best. We teach a language called beginning student language, and as Susan said, we're trying to remove barriers in CS. A lot of students ask us, why don't we just learn Python? Why don't we just learn Java? That's an industry standard language. Why are we, doing BSL? And the answer, there's a few answers. One is that it removes imposter syndrome. We're putting everyone on an equal playing field, a level playing field. And so the students who are new to computer science really appreciate that. And from week one, we start writing simple functions and learning language constructs, which doesn't take that long because BSL is pretty easy compared to things like Java or Python that come with a lot of libraries. Okay, next slide, please.
Do you see the next slide?
Susan, feel free to chime in. So week two, we start representing information in the world as data in the computer. So here we have a data definition for a traffic light. So light is one of red, yellow, and green, and we represent red, yellow, and green as strings, red, yellow, and green, and that's called a type comment. And then we have the interpretation, interpret the current color of the light, and then we have the template rules that gives us a template, which is a template for a function that operates on this traffic light data. Now, I'm trying to go over this and without you having to take this course. I don't know if any of you took the course, probably most of you haven't. So, you're not going to understand the whole thing because I'm trying to put it in 20 minutes, what we teach in 12 weeks. But well, what I'm trying to emphasize here is that representing data in a statically typed language like BSL, we do something called data definition so that students really follow the steps to represent the information in the world as data in a computer. And what that allows us to do is, like Susan, when we design a function like next color, which gives us the next color of the light, we first ask the students to follow the recipe and say, what does the function take in? What is it? What is the input and what is the output? Well, it consumes the light. It consumes the current color light, and it produces the next color light. So the signature would be light to light. And then we write a purpose, produce the next color of light. And after that, we write some unit tests. These are check expecs. We like to call them examples because this step of the recipe really gets students to think of cases, so that the more thinking you do in examples, the less thinking you have to do when you're actually coding the function body. So if you move on to the function body, so we have to define next color L. When it's red, we produce green. When it's yellow, we produce red. When it's green, we produce yellow. Sorry, when it's red, we produce green. And if you look, the template here kind of gives us a structure, the structure of the code. So all the students have to think about is filling in these ... so filling in these details. And really what we're trying to get students to do is not code line by line, not look at code line by line, and really focus on the structure of the program, and so that you only have to worry about the details when you actually need to. And a lot of students, ask us, can we actually go to the previous slide? Sorry.
Oh, yes.
We're not teaching the syntax of BSL. We did that in week 1 in half a week in one lecture. We're trying to teach students, going from a poorly defined problem to a solution. We're trying to teach them the process. And someone with programming experience would have went straight into coding the definition for next color right away, and they probably would have gotten it right because it's not a hard problem to solve. But instead, we took the long way. Instead, we said, you have to write the signature first, you have to write the purpose first, you have to go through all 3 examples, and then you can go into function definition from the template. And the most challenging part of teaching this course is these people with programming experience in the first 3 weeks of the course, because we have to tell them that what you're doing is so right, but maybe you should try to follow the process. Trust us, because the programs you're going to write in the later half of the course, it's going to be much harder. And this, we really want you to put that into your brain, so that because it's going to help you. Next slide, please. So in week 5 and 6, we move on to more complex forms of data, which is recursive structures, trees, and then later graphs. And many computer science curriculums in higher education go into recursive structures, tree, and graph recursals in the 2nd or 3rd year. And not all of them. Some do it in first year. I'm not saying that we're the only one, but our course is not like a major stream computer science course. A lot of different people in the arts, people who major in English take this as an elective. And we teach them graphs. We teach them how to write recursive code. And using the design recipe, we allow students to design the structure of the solution first, and then get into details. And we make that process much easier to manage. And that kind of the problem-solving process can help them with other stuff, not just computer science, which I'll talk about later. Next slide, please. Another important thing is that we really try to get the idea that we work with models of code, not line by line. And I say a key factor in distinguishing quality of developers, but I'm obviously an undergraduate student. I'm not going to say that proudly, but it's what the professor says. And it's a foundation for upper level computer science courses, which I can say because I took upper level computer science courses. And if you're building large programs, you're not going to read code line by line and say line 56 says this, line 57 says this. And that's not how you understand code. That's not how you read code. And type comments, which is what we saw before in the data definition, which I'll show you again, is a model of code. It's a model of the code, and it gives us a structure of code, exactly the structure of code, and it allows students to reason about their code in a model. And I'll show you an example right now. And this is from week 6 of the course. It says design a function that consumes 2 lists of strings and produces true if the first letter of the list is a prefix of the second, meaning that the first list matches 1-for-1 the beginning of the second list. For example, prefix in the first list is AB, and the second list is ABC. That would be true because AB is a prefix of ABC. The second example, list AB is the first list, and list BC is the second list, is false because AB is not a prefix of BC because A is not in the second list. The third example, list AB and list AB is true because the prefix of a list is a prefix in itself. The entire list is a prefix. The last example, list AB and list A is false because list A is bigger than list B. It can't possibly be a prefix. And when we look at this, it's harder for students who are coming from a programming background to code the function right away, right? This is where they kind of get confused. Some people might be able to do it, but there are harder problems that we ask them to solve, and they're probably not going to be able to do it. So we look at the type comment. Next slide, please, Susan. That's a type comment. Type comments are the model of the template code. It gives us what fun for LOS is. That's a template of a function that operates on that code. And we're working with 2 of these, 2 of the strings. So we ask students to create something called a cross products of type table, which is that. And this is a required part of courses, required part of our assessments. So an exam or problem sets, they're required to write this. And we're requiring to write a lot of things that are not necessary for the program to run, but it's an important part of design, the design process, so we ask them to write it. So you can see the list of string is either one of empty or const string list of string, and const string list of string just means a list that is at least one element, so a non-empty list. So list 1 is either empty or a non-empty. List 2 can also be empty or non-empty. So in the top left corner, that's when both of the lists are empty. Now, if both of the lists are empty, then is the first list a prefix of the second list? Probably, right? Because we said it in the third example there, a list that is this, if we get 2 of the same list, then that should be true. An empty list is a prefix of the empty list. So that top left corner would be true. And then we could think about, when list 1 is empty and list 2 is not empty, then would that be true? Probably, right? Because an empty list is a prefix of any other list. So that would be true. And then we think about when list 1 is not empty, but list 2 is empty. Oh, well, can that ever be true? Can a non-empty list be a prefix of an empty list? Well, list 1 is bigger than list 2, so it probably can't be a prefix. So it would be false. And the last case, which is the hardest case, is when they're both non-empty lists. But the template gives us the first of each list, because they're both non-empty lists, so we know they have a first element in both of the lists. So we could check if the first of the list matches, first of list 1 and first of list 2 matches, and then we could check if the rest of each list are prefix. The rest of list 1 is a prefix of rest of list 2. Now, this part is a little bit more complicated, but our students are able to solve this because they have done much more before we learned this. And this type of problem solving, we don't go into the function body right away, but we ask them to work in models. And I think this gives a very good introduction to when we move on to upper level computer science courses. And when I code in a different language and I solve a problem, I like to get a piece of paper and draw it out first, and that really helps me because code is difficult to read. That's why I tell my students, code is not it's not easy to read. If it were, then everyone would be writing it. Next slide, please. And then we label these cases 1, 2, 3, 4, and then we translate into code, which is what we see on the right. Sorry, what we see on the left. So if both two lists are empty, it's true. If this one is empty, it's true. If this 2 is empty, it's false. And otherwise, we check if the first matches and the rest is a prefix. Yeah. Next slide. In week 9, we go to search algorithms. So they've already done trees that operated on what we call non-generative trees or structural trees. Search is generating a tree, generating a possible solutions, and then operating on that. And we've already learned everything before that allows students to write search. So search is just an application of everything that we learned before. And using design recipes and data-driven templates, students are able to solve search problems like building a Sudoku solver. In our How to Code MOOC on edX, one of the videos or one of the set of the videos goes over solving search problems, specifically the Sudoku solver. It's a really fun set of videos, and I really enjoyed it when I took the course. And we work with models and abstraction, and we're not asking students to write code line by line. It's really easy to just say, here's a solution, and this is what the solution looks like, and that's what you should code. This is what good code looks like, and that's what you should do. It's really easy to say that as an educator. And it's hard to go through the process and tell them exactly what we do now and what we do next. And that's what we're really trying to focus on. And when we ask students to solve search problems, we first ask them to draw a tree. That's the first thing we do. Or before that, we ask them what does it consume and what does it produce and how we represent that data. But after that, we ask them to draw a tree. Next slide, please. Oh, actually, we were thinking of finding trees that students drew right before the presentation. We couldn't find
not
it
find
for
it.
some reason. But they're really adorable, and I wish I had some to share. This is what our students say. Studying computer science inspired me to think about problems differently and take a more systematic approach to them. Program design is applicable not only to computer science, but numerous areas of life. It is essential in the development of problem-solving skills. And my takeaway from taking this course and TAing for 9+ terms is that design is a domain general skill. Problem solving is a domain general skill. You can apply this in writing an essay. I wouldn't just go straight into writing an essay when I'm writing an essay for philosophy. I would think, do the brainstorm, follow the process, maybe look at some similar essays that other people wrote and take a note of their structure and use that structure to formulate my ideas. I'm not copying their solution, their essay. I'm looking at how they conveyed their idea, how they structured it, and use that so I can focus on actually delivering what I want to say. Because when people write code, it's not just in the industry. I don't know the industry, but we're not gonna tell students to just write everything all at once. They're gonna develop on other people's code. They're gonna follow a process, and that's what we're really trying to focus on. And yeah, next slide, please. So I know I talked about generative AI in the description of this talk. Of course, I don't know what's going to happen to the industry, and we're undergraduate students, so we should be the ones who are most worried about it as upcoming juniors. But all kinds of work is about to change, maybe a lot, I don't know. But it does seem clear that maybe in 2 or 3 years or less, software engineering, including interns, will need to be able to use like Copilot or similar to be more productive or produce more value per salary dollar. Either we will need to be used or we will be asked to use, I don't know. probably if that happens, then one part of that will be quickly evaluating code that an AI tool proposes. And the other part will be that, having a dialogue with an AI tool about the code you have written. But if you just know the syntax of what of Python, for example, what is the whole point of this? An AI tool is literally generating code that you don't really understand. You don't really know the structure of. And we believe that systematic program design gives students a foundation for that by focusing on design level constructs that exist across all languages and tools. And vibe coding. It kind of, I have seen students do that in the first 2 weeks of the course, but in the later half of the course, they kind of understand that this is really important. Not everything that ChatGPT gives them, they could just copy and paste and hope for the best. They actually have to be able to understand the structure of it. And in the end, it's that student copy and pasting. So they're responsible for their code that they copied and paste. Yeah. Next slide, please. Yeah. We prepared this presentation without knowing like exactly each and every one of you and what your backgrounds are. So I try to keep the presentation part short because I didn't want to be too niche about it. So we put this later half of the part for Q&A. If anyone has questions, feel free to ask.
So if you want to throw a question in the chat or just come off mute and ask your question. And if you don't have questions, I'm just going to grill them for like the rest of our time here. So if I got any questions about teaching systematic program design or industry careers, preparing for the unknown. I did want. Oh, go ahead.
I have a question. Sorry. So, how many of your past students have gone into industry and voiced opinions on what they've learned with this design methodology? I'm just very curious if it's been, wow, this has been really helpful, or because I did not learn this way when I was in college.
You want to try answering, Susan? Well, it's hard for us to answer because there's not a lot of people that graduated before us because we're also students. But so I'm going to tell you what I've heard, if that's okay. What I've heard is that this course offers a summary of what it's going to be like in second or third year computer science courses because we're working on graphs and trees and algorithm design, very introductory algorithm design. And a lot of that helps with technical interviews. And really, I think the upper level computer science courses I take that work on big projects, like big sets of code, it's kind of the same thing in terms of the process. It's just that it's bigger problems and a little bit more difficult problems. But the core idea of that is the same. So it really helped me in my upper level computer science courses to not, just to approach the problem differently in the first place so that it will be much easier. And I kind of remind my project team members about maybe we should do this first so that we can understand that. And I think my advice helped with them probably.
Cool. Thank you.
So yeah, that's a good question. I now Matthew and Susan are probably at a little bit of a disadvantage because the people that they're working with have not graduated yet, and they'll move on before then. But I've hung out with some of the people that have were kind of behind this this approach, Matthias and others, and seeing the kids that they were working with that were then finishing up their PhD and going to work at Google and things like that. And it was interesting talking to them. And the big thing I heard from a lot of them was they felt like they were more prepared than some of their uh, fellow students that were coming from different backgrounds in being very systematic. And kind of in talking to them, what I heard is it sounded more like if you talk to an engineer that's building bridges and then you talk to a typical software engineer, they are not doing the same thing. It's very, very different. You know, one's like, let's try this and see if it works, kind of. And then you got the engineer building a bridge. It's like, no, we know if I follow this process, the bridge won't collapse. And these individuals I was talking to felt like they very much had the approach of an engineer who's building a bridge and just knows if I do this step by step, everything works, instead of maybe trying things. I was working with some electronics, and a friend of mine came over that was a electrical engineer, and I tried something that didn't work, so I unplugged it and plugged it back in. And he's like, "Oh, you troubleshoot like you're a software developer." I was like, "Well, yeah, that's that's it." But it kind of made me realize the difference between some of those things. But okay, Christopher Lynn asked, have you seen non-CS students reach that aha moment and develop something in their own field of study?
Well, I have one example. It's about templates. So we talked earlier about templates and how only students have to focus on the details. And I kind of talked about that in the last slide too. But when you're writing a resume, or when you're writing a cover letter, and when I'm doing that, and when my friends are doing that, we're not just going to write the resume in our own format. We download a template to do it. And, you know, that might sound not genuine for some people, but really that allows me to focus on what I really want to write in my cover letter and what I really want to write in my resume. Because I don't have to worry about formatting. I don't have to worry about the nitty-gritty details of it. So that's one example that really comes to me personally, about templates, about trusting the process, trusting the thing that already works. Susan, do you have anything else?
Sorry, I was looking for the unmute button. I haven't really heard much about the projects that our non-CS TAs go into doing after they've taken the class, but I do know that a lot of them take or like end up pursuing more technical things on the side anyways, and they take a lot of the applications they have from the course into like the different pursuits they have on the side. In terms of like an actual something that they developed, I can't name you that, but that's what I've noticed. A lot of people that I've talked to who like have graduated from the class, they mention just the way that they've changed how they've even approached their various projects. And it's really nice to hear.
So my son and I did the online version at edX that I posted a little bit here earlier when I can't remember how, I think he finished when he was 14. So he was probably, I think, 12 when he started or something like that. And a couple things that I noticed from it was, see, he turned 16 this weekend. He's doing Calc 2 in high school. And it was interesting for me to see that there seemed to be a huge overlap between the stuff he learned from the class and the ability to think more abstract mathematically, which now he realized, and he doesn't want to do software development. He wants to do math. How do you put it? Math. If it has a practical application, that's not the type of math he's interested in, which hopefully will change when he tries to get a job at someday. But anyway, that's what he's interested in. But it seemed to give a foundation for very the ability to think in abstract ways that I don't know if he would have gotten another way. The other thing I noticed is the other day he was reading about there's a sculpture in the middle of, I think, the Pentagon called Kryptos that like several panels have been solved and one of them hasn't been solved. And he got an idea for, oh, here, I think I've got an idea to do this. So he doesn't want to be a software engineer, but now he's got a tool set of doing programming. So he pulled out the, Dr. Racket and started programming stuff in it to try to solve. I don't think he solved it, but it was interesting to see how naturally that came of this is just another tool to try to solve problems with. Somebody asked, let's see, Jeff asked, how much do you feel the course parallels the How to Design Programs book by Matthias and the rest of them?
Yeah, so the How to Design Programs book is a basis for systematic program design. So we took some parts that we found were would suit our students, and we found some parts that we thought wouldn't suit our students. And we basically developed on that and focused more on the systematic process of designing programs. The How to Design Programs book, I haven't gone through the whole thing, but I've skimmed through it. There may be a little bit of math that involved, a little bit of complex time complexity, and I've looked at the University of Waterloo, which is another good school in Canada for computer science. They teach how to design programs, and they have a lot of more math involved. But our course, we don't have any math because our students are diverse. So I do think it covers the essentials of the class, but you might not see it from the entirely same perspective. But it's still a good curriculum. If you like reading books, I would follow it.
I think one difference I noted, and I haven't gone through the entire book, but one thing I did notice is the class does a very good job of giving you a bunch of, at least the online version, give you a bunch of parts and then let you put them together into something that you can be proud of and show people. Like, I think you guys still do the Space Invaders game?
Sadly, we
like
do
that?
not, but I've seen
You
it
don't?
before.
Okay. So here is I'll throw it in thing. This is the one that my son did. But what I was impressed with was the pedagogy of going through and you build a bunch of things that are interesting in their own, not super math based, but we're gonna make rain fall, and I'm not sure which of the. But then when you get through, you take everything you learned and put it together into something that was actually fun to play with. And I don't know if the textbook. I think the textbook is a little bit more meant to be used independently from the stuff I've seen. So that might be a difference, or if you're wanting to explore the difference, that might be something to look at. Laura Chang asked, while I understand the value of following a process that works, how much of this process has been iterated and improved? So maybe kind of talk about the life cycle that's gone on so far in the systematic program design movement. Like how did you guys get where you're at today, or at least the parts you know of? It wasn't just like, here's what we're going to do, and you've been doing the exact same thing for the last 10 years, right?
Yeah. Well, first of all, we haven't started programming in the past 10 years because we're still young. So we might not know the entire history of systematic program design, but we've I know the parts that we have improved on, which is the autograder and tags. So when we Susan, can you go to one of the slides before, one of the code slides? Yeah, before that, maybe week 2. Yeah, if we have here, we have the signature tag. So the @, these are tags. And these provide, it's a statically typed language, so it doesn't really matter, but these are metadata annotations. And when we submit to the autograder, it gives you feedback. So we really try to give feedback on the steps of the recipe that students might be incorrect. So exactly where they went wrong. Although those don't have anything to do with how the code runs, it gives checkable design information. You're leaving notes, you're leaving little breadcrumbs on which steps you followed. So as TAs, we look at the tags and see, oh, maybe you went wrong here. Maybe there was some misunderstanding here. I know this didn't really answer your question, but these are the improvements that we've been making in the past few terms. And I think this has been great so far.
So what is the students in the class, you mentioned an auto grader. So is this something that's helping them grade their homework, or are you grading tests like this? Like, what does that look like for a student?
So all of our problem sets and our exams and labs are mostly auto-graded. We have some TAs looking at them because we want to emphasize the idea that another human being is going to read your code, and you want your code to look good. You want to indent your code properly. You want to style your code properly. And that's why we still look at the code. But we want students to get constant feedback because there's only 50 of us and there's 1,000 students. and we're not there at home with them. So when you submit to the auto grader, it tells them in order of the recipe, signature incorrect, and then everything else. And we ask them to look at it in the order because there are additional tests that run against the student's submission, and that tells if their code is actually working or not. But really, you shouldn't look at that first if it says your tests are invalid. Because if your tests are invalid, your examples are invalid, that means you're understanding the problem incorrectly, right? So we really try to get them to look at it in the order of the recipe. And I don't know if they do, to be honest. Some of them just ignore it. Some of them they're like, oh, my function's not working. That's the most important thing. And we really try to get them to read it in the order of the recipe. And those students usually do far better, in my opinion.
To add on to that, like we don't want the students to develop a dependency on the autograder, obviously. But a lot of the reasons, at least with our current improvements, a lot of the changes that we're making have to do with the autograder because we recognize that the best way students respond to feedback are by looking at their grades, and they're pretty motivated to see like their grade go up and go down. So we adjust accordingly to present information that they can learn through the autograder. So a lot of what we're putting into that is trying to separate it out by design elements so that they're not just looking at getting 100%, but it's like a breakdown of them following or not following the design steps. And I think we're past the era now of going through iterations of the checklist. So we weren't there, unfortunately, when Gregor came up with the idea of the design recipe checklist.
Yeah.
So it sounds like what you're saying is it's not just a matter of I took a class years ago and it was some guy that worked at Yahoo, and he it was years ago, and it was on Perl, and he basically said if you can pass all the tests I run against your code, I'll give you at least a C even before I look at it. But those were just testing the code. No matter how, you can do some pretty crazy stuff in Perl that's like impossible to read. It sounds like your auto grader is actually saying, have you followed the process? And then it does have some TTD tests, but the big thing it's checking for is, have you used the design recipe correct? Do you have the check expecs and those types of things? Is that what it's doing?
Yeah.
Okay.
So the additional tests, they're only worth like max 30%.
Okay.
So, you know, if you make a code that works, you got 30%, but that's still a failing grade. The rest, 70% is everything else.
Okay. So back to the engineering example. If you build a bridge and you can get a really heavy truck across it, is that success, or can you actually prove that you followed the process correctly and it's not going to break from? Okay. How do you deal with testing? Because a lot of the presidents of different universities and things I've heard talking about with Chat GPT and stuff, just trying to figure out how to make homework matter in ways that it's not giving students the flexibility to use new tools that they're exposed, that they've got access to, but still make sure that you're testing to make sure they actually have understanding. How do you guys approach that, particularly like on the homework and stuff?
So we have face-to-face grading of problem sets after the auto grader. So in labs, we ask them to bring their problem sets with them, and we ask them a bunch of technical questions to see if their vocabulary is right and to see if they actually produce their solution instead of copying someone else's. And we could tell most of the times that they understand the problem set or not, if they understand their homework or not. And that's also part of their problem set grade, I think 25%.
Okay.
It's an ongoing battle. It's something that we're constantly trying to work with like our misconduct TAs on figuring out ways to work with it.
Okay.
But for the most part, like our approach right now with assignments is like I try to reinforce that the students are like really to drive in the fact like what we're trying to teach the students when we have them do these assignments of like we're trying to encourage them to have to struggle on their own and come up with and like make those crucial connections that they have to make by staring at something for 20 minutes and not having someone interfere. And obviously it's not going to hit everyone, especially the ones who are reliant on the tools, ChatGPT and stuff. But there are things that we have to constantly think about. And currently those are our like strategies.
Okay. And it does seem like you're emphasizing here's the process you need to go to, and whether you're like the 30% for the test. That's important, but that's not the thing you're trying to teach here. You're trying to teach here to follow this process, which maybe can rein some of that in. But yeah, that's a big struggle in a lot of places, I know. Let's see. Okay, somebody posted something about ACM Code of Ethics about the process. That was a good point. Anyone else have any questions while we've got the experts here? Well, so this is fascinating to see what you guys are doing, and I really like the approach. The little bit that I've seen about it, I wish that existed when I was taking computer science classes, but I've been able to go back and grab some of it, and I definitely see the value of a lot of this. So that's absolutely great. Well, thank you so much for coming today. Would you one other question? What advice would you have from kind of what you're seeing and hearing and being in the academic circles you're in? Um, if somebody's got a upcoming teenager that's in high school, because I know this has come up with this group quite a bit, and they're thinking about going into computer science, what types of things would you suggest they do in high school um, to kind of prepare for that, or to see if they're even interested in that, or would you say no, don't do it? Don't do computer science. What type of advice would you give to somebody that's kind of trying to figure out how to advise their teen that's in high school that might be interested in a career in computer science?
Well, to be completely frank, I don't think I knew particularly that I wanted to go into computer science in high school. And it certainly wasn't something that like my parents pushed me to do. And I think I'm very grateful for that because I think that too much pressure interference, especially if like, for example, if your parents are working in computer science or like a field, you kind of sometimes don't want to go into that same field. Um, I think just for me, I just explored like a lot of like just as many things that I wanted to try out in high school. So like my high school did advanced placement classes, so I just took as many classes that I wanted to just to see the different types of courses that are being offered. Um, and just doing like different extracurriculars. I think so. I think my advice is don't push too much on on trying to get them to try things because that could just do the opposite and repel them away from it. And yeah, I don't. I guess my parents didn't really say much when it came to my high school career, so I just ended up here in computer science. Matthew, if you have other advice.
Well, computer science is a big field. There's a lot of subfields in it. So, I would say try a lot of things. I think that's kind of opposite of what Susan said, but try different things. There's a lot of things you can try. You get to work with a lot of different code, a lot of different domains, and really try to figure out what you like, what you enjoy. And I've been trying to do that myself, and a lot of students get different internships in different fields so that they could get they're trying to figure out what they like while at university, and you can still do that when you're in high school too.
Cool. Well, if no one has any other questions, thank you, Matthew and Susan. Thank you so much for coming. I see there's a chat here. Roger saying thank you so much for you guys coming because he's got a high school senior in high school looking at some things and was very appreciative of you guys taking the time to talk to us. So thank you so much for coming. Really appreciate you taking the time. This was really interesting to see this stuff, and good luck to you because I think you guys you're finishing up your senior year, right? Both of you? Okay. Well, good luck in your future endeavors and job search. And thank you so much for coming. And thank you everybody else for being here. Next week we have, let me make sure I'm telling everybody the right thing. We're going to be talking about projects versus products in managing software, like the different mentality behind that and how that can impact the way that you approach managing software projects. So if you know of anyone that's on your team that might be interested in that, forward the invite on to them. Once again, Matthew, Susan, thank you so much. And best of luck in your careers.
Thank you for having us.
Thank you.
Thank you everyone
Thank you,
for coming.
Okay. Goodbye, everybody.